Okay, welcome everyone to this continuation of, my lecture series on the analytic theory of monoidal categories. Keep in mind, or note better, not keep in mind, that this is part 2. So if you haven't seen part 1, this is what I'm going to say. It does not necessarily have to make sense, okay? So, anyway, so it's my idea of strategies to avoid counting, or the idea, not my idea, the idea of strategies to avoid counting. So we are trying to find various ways not to do the count, and I kind of gave you in the previous video several examples of how to not count. Sometimes counting is difficult, and today I would like to explore this idea of exponential growth. Here's one of my favorite XKCDs. So exponential growth starts off a little bit slowish, but yeah, it's exponential growth, so it grows fast. So whatever, under control, going down, yeah, maybe not. It's always exponential growth. And today I really like this picture because today we essentially always have exponential growth, like always exponential growth. And I promised you to zoom in into one specific problem, and I will tell you essentially all I know about that problem. And yeah, to get started, let's start with a not counting, or let's start with a log plot. So a log plot, as usual, is taking a log on the y-axis in particular. So this here is 1, 10, 100, right? While this goes 1, 2, 3, 4, 5. So this is a log on the y-axis. And in a log, you need to take a log on the y-axis. And in a log plot, a line is actually exponential growth, because that's how it works, right? 1, 10, 100. So a line is exponential growth, and whatever looks like a log is actually linear, and well, 1 to the n is of course boring. And kind of the point of my story is that I will call all of these guys here exponential growth, where you have something exponential and then some correction term. Because as you can see in the plot, now the correction term pushes it down a little bit, but eventually they kind of grow all in the same slope, if you want. Because compared to exponential growth, the correction term, like let's say n or n squared, doesn't really do so much. So polynomials will not compete with exponential growth. Just keep that in mind as we go along. So polynomials, you have no chance against exponential growth. Kind of the point here. Okay, before I give you more details, there will be some more details later. But let's say gamma is something that has a tensor product. So the only thing I want to do is I want to make sense of my problem. So I take something, let's just say a representation of a group, and I tensor it n times, and I want to decompose it. So I have this idea of, the theory of monoidal categories, and the one operation you can do in a monoidal category is you can tensor things. So it's kind of the crucial operation, but usually, like the indecomposable summons or something, they're invisible in the same sense as the prime numbers are invisible, but they're still the main players. So I will try something like that. So we want to decompose this tensor product into irreducible summons. And note that this tensor product actually grows exponentially. Dimension of the tensor product is just a dimension to the n, so this is growing exponentially. Huh? Okay, and in this generality, where I work over any field and I take any representations of my group or whatever, and I have any group essentially, there's not much I can say. Just to give you some idea, if k would be the complex numbers, and gamma would be the symmetric group, and v would be some rep, doesn't really matter which one, some rep, this problem is known as kind of the Kronecker problem, and it's like difficult, really difficult to say something explicit, even in this little tiny case where I have the symmetric group. So in this generality, there's just simply nothing I can tell you about this problem beyond some very basic stuff. Like, yes, the decomposition makes sense. I can't say much more in this type of generality, right? So I can't really say anything more. And just to give you some examples of what gamma could be, because it could be very, very general. So essentially anything you can cook up. Any group, any monoid, any semi-group even. So it's very, very general setting, even super versions if you care about those. And later on, we see that you can even generalize even more, and essentially you need no assumptions at all for my favorite theorem here. No? So it's kind of a really general setting. I will be more precise later, as I said. For now, just gamma is like anything where the problem makes sense of decomposing v to the n, because that's what we want to do. We want to decompose v to the n, so anything where that problem makes sense. That's what gamma could be. And really, in this generality, there's nothing I can say. Decomposing this is not going to happen. It's exactly like the type of questions we had in the previous video. So we need to come up with some better questions. Some questions we can actually answer, instead of having a question where we have no chance to answer it to begin with. And this is where my asymptotic idea comes into the game. So maybe it's better to go to plan B and not to decompose that space, but to play the following trick. Or let me remind you what we are trying to do. Well, counting primes is difficult. It's really the same analogy, but you can still write down this beautiful asymptotic formula. So where the indecomposables in my setting play the role of prime numbers, they're invisible in n, right? You kind of need to decompose n to find it. And similarly, the indecomposables are invisible in my decomposition. So, and what I told you is that the ratios get good. So this is really kind of not doing the count, because the difference can be still arbitrarily different. And I really care about the ratios in this type of question, right? So I care about the ratios. And I told you about people have done this, kind of looking at tables, and they came up with this idea of that counting is difficult, so we kind of need a different approach. And what I'm trying to kind of motivate in the last video is that discrete statements can often be solved asymptotically, and very often the answer is actually quite nice. And this is, kind of the underlying story, the underlying idea of everything I'm talking about, essentially. Okay, I hope that makes sense. Was a reminder. And now let's look at how to reformulate our problem of decomposing the space into the primes, which are the indecomposable summands in this decomposition, right? The indecomposable summands. So what did we do if you want to mimic the prime number theorem, the idea of analytic number theory? Well, we maybe should just count the number of those. Count the number of indecomposable summands. Count them with multiplicities, yeah? So what could happen here, for example, you can do something like SL2. You can take the complex numbers and the defining so-called vector representation of SL2. This is really where SL2 acts as matrices. And you write down the sequence. Okay, fine, whatever you get. 1, 1, 2, 3, 6, 10, whatever it is. So the zeros tensor power, just a round field. The first tensor power is what it is. The second tensor power, so c squared, let me just write it like this. I should write probably tensor squared, is a three-dimensional representation, a dim3 representation, and a dim1 representation. Yeah? So together they have dimension 4, so that works out, and this is the number 2. And then you keep on going, 3, 6, whatever. And I do the following trick, and you will see later why I want to do that. So I take my sequence, and I expect exponential growth, because my video is about exponential growth. So I expect exponential growth. And whenever you expect exponential growth, you kind of should do the opposite operation by taking the nth root. So I take the nth root of my sequence, bn, and it seems to converge to 2 in this case. So it's a 1000th step is like 1.99265. Okay, fine. What is 2? Well, 2 is the dimension of my space. Could be a coincidence. Who knows? But that is just what comes out. And here's a log-log plot, by the way. A log-log plot is you also have a log on the x-axis, not just on the y-axis. Convergence rates here are really, really slow. So here's my nth root. And you can literally you could see that it converges to 2. It does. Yeah? So this is the thing of the nth root. Fine. Maybe you keep on going. Maybe you try the 3-dimensional representation of SL2 just on the symmetric space. Maybe do the same. Decompose, same problem, right? You get this sequence 1, 1, 3, 7, 19, whatever. You take the nth root, and at the 1000th power, you have 2.98 something. So it seems to converge to 3, which, wow, is actually the dimension of our space. So there seems to be something we can say. So the dimension of our space here appears as like the leading growth rate of my function. That's interesting. That's somewhat interesting. And then something I've learned in my life is, I call this observation 1. So whatever is true for SL2 is kind of true in general. That's very far from really being true. But let's just make this an ansatz. Let's just go for it. In this following generality, for any affine semi-group superscheme, if you don't know what it is, doesn't matter. Just think of it as like a group. Any field and any representation, we count this number that we just counted for SL2. Kind of same setting, right? So analog of the prime number theorem. We count the number of summons. Okay, and the reason I really want to take the nth root is a certain type of lemma which is called Wittekes subadditive lemma, just in the multiplicative sense, where this equation actually implies that the limit of the nth root is well defined. So I want to find this value beta, which is really like saying what is the leading growth rate of Bn, of my sequence Bn, the sequence Bn that I would like to understand, the sequence pi, right? The sequence analog. So Bn is the analog of pi n. And that's the thing I would like to understand. Okay, and observation 3 is, okay, beta cannot be smaller than 1. 1 just means it's indecomposable. You have one block. And it also can't be bigger than the dimension of the space, because the overall growth rate of the tensor power, remember, that was one of the first things I actually said, the overall growth rate of, too many slides, the overall growth rate of the tensor product is dimension of v to the n. So this is like the upper bound that comes up just from this dimension consideration. So beta is somewhere in between those values. And they are kind of two different extremes. If beta is 1, then essentially everything is one block. If beta is dimension, then it's kind of the opposite. Every summand is essentially one-dimensional, because it's like the finest split you could have. Yeah? So it's either the 1 or the dimension. And kind of here comes something that I really learned, something that is even true, not like my observation 1, but something that's really true. I said a lot of statements take a 0-1 type thing. So it's either 1 or dimension, and it's very rare that it would take anything in between 0 or 1 type statement. So it's either one block or everything is essentially one dimension. And the fantastic theorem, like, again, we can't do anything in general, but if you want to really do something very explicit, but in this, really just asking about the leading growth rate of an asymptotic formula, this is what's happening here, you can show this fantastically general, absolutely ridiculously general statement that it's always the dimension. The growth rate is always maximal. Always. Which really means for anything, the indecomposables are always very tiny. They're always one-dimensional compared to the exponential growth of the tensor power. This is, I call this the beta theorem. It will appear several times because it's just so easy and it works in this ridiculous generality. Yeah. Again, keep the prime number theorem in mind. It's like something you can say, and it's actually a beautiful result. At least I think it's pretty good. Right? The dimension is always the leading growth rate of an asymptotic formula in ridiculous generality. Dimension is always the leading growth rate of an asymptotic formula. And this is just is just really, really, really good, right? Exponential growth is scary. Compared to the size of the exponential growth of this beast, all indecomposable summons are essentially one-dimensional. So if you have your sun and you think of this as exponential growth, and your question is how many planets can you fit into the sun, then you get a feeling for this type of answer that you get here. You could fit in many, many summons into the sun. And this is like a very general thing. It's kind of really nice. I like it a lot. I call it the beta theorem. Yeah, beta theorem. I hope people like it as well, because it's so general. I didn't even explain how general it is, because I didn't tell you what an affine semigroup superscheme is. Doesn't matter. It's like really, really, really general. Any field, any finite dimensional representation. Kind of essentially the minimal assumption where this question somewhat makes sense, and it works out like this beautifully, where you simply get dimension of the space to the n. Really, really simple. The beta theorem. Exactly what I was looking for. A nice answer to a question, and the answer is given in asymptotic type of thing. Okay, and the next step would be, well, remember my 3 questions. Tell me about the dominating growth rate. I just did that. In general, it's a dimension. Tell me about the asymptotic would be section 2. So I will tell you about the asymptotic. And essentially look as follows. This is a formula you see very, very often in the theory of, well, asymptotic approximations. It should be the overall growth rate. We already know that is the dimension, and then a correction factor that depends on n, and a correction factor that is independent of n. Like a scalar type thing. So an n to the something, a polynomial, and a scalar type thing. Right? That's essentially what it should be, because both of these are actually killed by the nth root. Right? If you take the nth root of a polynomial, it converges to 1. If you take the nth root of a scalar, yeah, that's very boring anyway, it converges to 1 as well. So this is the ansatz I take, and I'm going to describe what h and tau are for you. So in general, I have some formula that looks as follows: h times n to the tau times beta to the n, and I already told you what beta is. It's a dimension. So I'm going to tell you what tau and h are as well. Hope that makes some sense. Cool. So let's start with finite groups. Characteristics 0. Semi-simple case, complex ground field. So what you can do is, the character table is prototypical representation theory. So here's a character table, and we already had that last time, same type of character tables. Columns are the conjugacy clauses, and the rows are the simple representations. So here S3 and S4. Kind of same setting as in the previous video. Okay, very good. And how do you take tensor product in the character table? It's really easy. Let's say you take the tensor product of the third representation with itself. Then you just take the corresponding row vector. Here it is. You square it entry-wise. Here it is, right? 2 squared is 4, minus 1 is 1. And then you decompose it in terms of the other appearing things. So you get a decomposition into the first, the second, and the third. And then we count the total number of those. And I just encode this in the 1, 1, 1. Right? First appears once, second appears once, third appears once. And then this makes sense. It's just how the charactering works. Anyway. So this is how you do the calculation. So you take some row, take its nth power by raising every entry to the n, and then decompose it in terms of the other rows. Right? And you count the total number of summons. So in this case, it's just what's happening. And if you do this, and you do this for the standard representation, which is this guy here, in case you don't remember, this one is a dimension. So the 3 representations are of dimension 1, 1, 2. So I take the 2-dimensional one, I do it, and you can actually write down what the sequence is here, the sequence of 1, 1, 1s. It's 2n over 6 essentially, or 2n over 3, depends a bit whether in what entry you look. And in particular, the formula itself up to this rounding, which you can ignore, because that's a nice thing about doing an analysis or analytic asymptotic analysis, is you can ignore those fluctuations. Rounding, who cares? Who cares about rounding? And you will get a 1/3, right? 1/3 plus 1/6 was plus 1/6. 1/3 plus 1 over 6 plus 1 over 6 is 4 over 6. That's our correction term. Nothing going on with n to the 0. I just write it out because that's what I wanted to do. I wanted to find tau. N to the 0 is 1. Doesn't appear. I just write it out as n to the 0 because tau is 1. I have my ansatz formula here, and the dimension is exactly what the overall growth rate is exactly what we think it would be. And convergence here of the ratio is actually really, really fast. Okay, so what happened here is we got a scalar, our overall correction term, and the tau is 0. Well, I just write into the 0. Cool. Let's do the same for S4, and let's say we take, well, the fifth representation. Why not? And to do the same, you square everything and you decompose it in terms of the others, you get something. Okay. You do this analysis, not difficult, you can do it yourself, and you will find that it's 10 over 24. This guy is still 0, 3 is the dimension. Okay, so let me just write it next to this table here. 10 over 24 was our number, and 3 was just the dimension. And here, our number was 4 over 6. And now I'll give you a second to find 4 over 6 in this table. So 6, you probably will come up with this quickly if you just look at the examples. It's the order of the group. Okay. So 24 is the order of the group. Oh, yeah, not too bad. That's easy. 24 is the order of the group. What is 4? Well, you stare at it a little bit and you will realize it's not difficult to see, but maybe I help you. Just take the sum of this first marked column, 1 plus 1 plus 2, and that's 4. Aha. So the sum of the dimensions of the simple representations. Okay, let's have a look here. 1, so we take this first column again. 1 plus 1 plus 2 plus 3 plus 3. Yes, that's 10. So conjecture is, our formula should be, the asymptotic formula, should be dimension. We already know that. That's a beta theorem. This one is boring. It just does nothing. This one. And this one is kind of the sum of dimensions. Maybe I change color. Give me a second. This one here is the sum of dimensions. So first column of the simples divided by the order of the group. Okay, that would be the conjecture. Fine, and we just got that from this calculation, yeah. And indeed, for any group, let's say under a certain assumption, I will tell you the assumption in a second. Namely, you want a faithful representation. I will tell you in a second what that means. But anyway, for any group with this property, which forces it to be faithful. So the first value appearing here is bigger than everything else. Yeah, so it works for all of these. Doesn't work for those guys. And by bigger, I mean absolute value bigger. For all of them, it's really just the formula that you take the sum over the first column. That's it. That's this guy here. The sum of the squares of the first column is the order of the group. And then just the dimension to the end. Again, a really beautiful answer what it is. You can just read it off from the character table. Yeah. So sum of the first column over sum of the first column squares times the dimension of the representation is the asymptotic in this case, which is, like, I think, a really, really nice and beautiful answer. And yeah, so this is almost true in complete generality. The only thing that kind of can spoil the story is if you have this guy appearing like twice. The first one, and then it repeats, and the formula is not much worse. And just do it. If you do it for the dihedral group, you will find this type of behavior. So 6/8 plus -1 to the n times 2/8. And the reason is now those two guys will kind of compete with one another if you take the nth power, but they will go hand in hand, depending, or compete depending on the power you take. And in this case, the formula looks as follows. Let me just write it down. 6/8 and 2/8. 6/8 and 2/8. So 8 is the order of the group. So 8 is just the order of the group. All fine. So this guy here is 6. 1, 1, 1, 1, 2 adds up to 6. And this guy here adds up to 2. There you go. So these are the two scalars that you get. So just take the first entry. Nothing can ever be bigger, strictly bigger than the first entry here. But it could appear with the same absolute value. Just take the ones where it appears with an absolute value and add those columns as well. And that's the general formula. So it's not terribly difficult. The only thing you need to be aware of, if you have more of them, you add them. So in this example, for example, you would have those three that you would need to add together. And then you get the corresponding third root of unity. So -1 is the second root of unity. So if you have 2, you get a second root of unity. If you have 3, you get a third root of unity. If you have 4, you get a fourth root of unity, and so on. But otherwise, it's just the corresponding column sums divided by the order of the group. And you kind of can really see that in the behavior, because in this case, it's kind of, they compete, they go hand in hand, they compete, they go hand in hand, they compete, they go hand in hand. So what do you do? Well, really just take everything that repeats. That will be the order of the group. Take the corresponding column sums. That's your asymptotic formula. This guy is boring. Just one. This guy is a beta theorem. It's beta, and this guy is given by column sums in the character table. A completely explicit answer for any finite group and any finite dimensional representation of it. It's ridiculous that it is just a closed formula for any finite groups. It's very remarkable. It's not difficult. Yeah. Yeah. So if it's not faithful, find the kernel and repeat. I'm not going to explain how that works. So it could have something like this. But there's also a closed formula for that case. I'm just not stating it right now. Anyway, so let's try it. So let's say we have this character table here. And what is the growth rate for the marked representations? So here, I haven't explained the blue one, so let's skip the blue one, but let's do the purple one. Well, the purple one has a 3, so we have a 3 to the end, definitely. And it has a -3, so you need to take this column sum and the other column sum. And whatever it is, 1, 1, 1, we'll do it. I did it anyway. So for the purple one, it's 20/48. So 48 is clearly the order of the group, as 4 cross z mod 2. And this column sum is 20, and this column sum turned out to be 0. So can we see that 3 and -3, they cancel, these guys cancel, these guys cancel, these guys cancel. Yep, and that's then your formula. Really easy, right? So here's another one. Let's do it. Let's say for the 7th one, what do? You take the order of the group, which is in this case 168 as far as I remember. Fine. This doesn't repeat, so you just need the first sum. The first sum is 10, 10, 26 as far as I can tell, and that's your correction factor. N to the 0 and 6 to the n. That's really good. That's really one closed formula that works for any group, any finite group, any representation of it. Really remarkable. It's really, really remarkable. And in particular, kind of this fun fact that this correction term does not depend on the representation. It's something you read off from the group, from the character table. Does not depend on the representation. That's a very surprising result. Anyway, you can even say more. You can say something about the variance, the Riemann hypothesis. The only thing you need to do is you need to look at the second largest entry. So in this case here, the largest one is 6, the second largest one is, again, absolute value is 2, so the variance is bounded by 2 to the n, which is like really good because it grows like 6 to the n, and so the 2 to the n is actually not that much compared to 6 to the n. So you can also answer all questions explicitly in this generality, which is like exactly the story I want to sell. It's remarkable, really remarkable. So what actually changes if you do, might ask, okay, you did character theory, characteristic 0, complex numbers. What actually changes if you go to characteristic P? Nothing. Kind of interesting. So if you do characteristic P, let's say Z mod 5 over F5, you have 5 unique opposables. They correspond to those little Jordan blocks. And the dimensions of them are 1, 2, 3, 4, 5. Only one of them is simple, only one of them is projective. So this one is a simple one. This one is projective one. And then you have this blurry in the middle. And you can ask exactly the same type of questions. Yeah. So for Z1, nothing is going on. It's boring. For Z5, Z5 has a very easy multiplication rule. It just spits out 5 copies of itself. So the overall growth rate is 1 over 5 times 5 to the n. And it's multiplied with itself. It spits out 5 copies of itself. There's an offset because you start a little bit late, one later. So it's a 1 over 5. For Z mod 3, you can do the analog type of thing, and you will get exactly the same formula. That's already interesting. Just you have 3 over n, right? Because that's the dimension. So this term is again independent of the representation, as long as it's faithful. So this one is kind of boring, and the other one is just the beta from the beta theorem. Interesting. So what is 1 over 5? You might wonder here. So let me just write it down again. So there's 1 and there's 5. So 5 is clearly the order of the group. It's still the order of the group. And what is 1? 1 is still the same as before. The dimension, the sum of the dimensions of the simple representations. Same formula. Is it a coincidence? Of course it's not. It's just really the same formula. There's essentially no change if you go to characteristic P. So if you do, for example, SN2FP, you will end up with this formula, and you can kind of do the same thing. And the order of the group, in this case, is here. The sum of dimensions of simples is this guy. So the ratio is exactly the number you see up turning up here. Wonderful. So it is, in general, really just that. It's kind of remarkable. So my formula does not just work for characteristic 0, it works in complete generality for all finite groups and all representations. And I call this a very inclusive theorem, so very nice. Equality, diversity, and inclusion, very inclusive theorem. I'm very happy. So for any finite group, and there's no difference, essentially no difference between characteristic P and characteristic 0, our formula is still given by the dimension of those guys is the same, and the correction term is still dimension, sum of the dimensions over the order of the group. And there's also a version for the variance, which I haven't bothered to write down. That's a very inclusive statement. Yeah? So that's the whole mantra I'm trying to sell here. If you go to the asymptotic setting, you get really nice answers, very general answers, where you have essentially no hope to do that in any more explicit form. And you get really, really good, very good theorems. Here, this very inclusive theorem. So let me just pull up this example, but we'll skip it anyway. And you can also read that off from the character table. So this is really, really good. It's very inclusive. You could actually do the same for any finite tensor category, not just for representations of a group. For any finite tensor category, any characteristic, it's remarkable. You just need to replace dimension by Cohen-Frobenius dimension. But we don't do this in this video. I just want to highlight the point that, again, this is like very inclusive. Like very inclusive. Like it's true in kind of complete generality. Anyway, I hope you enjoyed this video, and I also hope to see you next time.